Here's an example about stationary points and the nature of the stationary point. When it says determine their nature, we really want to know, is it a maximum, is it a minimum, or is it a possible point of inflection? I say possible point of inflection for a reason, and we will, like I said, come back to points of inflection later. So the first thing we need to do to find a stationary point is to differentiate the function. I'll just write the function again here, minus 12x squared plus 2. So the derivative of that function is 3x squared minus 24x plus 0. And we want to know, where does that equal 0? Where are there any stationary points? So I'll factorize this. 3x out the front, x minus 8 equals 0. So either 3x equals 0, which means x equals 0, or x equals 8. We must find the y coordinate by substituting these values back into the original equation. If I put 0 back into the original equation, I'll get 0 minus 0 plus 2. So for that one, y equals 2. For this one, if I put 8 back in, 8 cubed minus 12 times 8 squared plus 2, I get y equals negative 254. So those are where the stationary points are. Now I need to determine their nature, and we do that with what we call the first derivative test. We are going to learn about the second derivative test later in the chapter, but for now we're just looking at the first derivative test, and that's very much like what I showed you in the example from the theory notes. We draw up a table, we've got x, and we have got the first derivative. In the middle is the x values of our stationary points. So the first one was x equals 0. We want something a little bit to the left of 0, fairly close to 0 preferably, so I'm going to go negative 0.1, and something to the right of 0, so I'm going to go positive 0.1. And we substitute each of those numbers into the derivative. Now if I put 0 back into the derivative, this line, the derivative, I'm going to get 0, because that's what we solved for. If I put negative 0.1 in, I'm going to get a positive answer. And if I put 0.1 in, I'm going to get a negative answer. So if I draw the gradients of those, I have positive, I have 0, I have negative. We can see that is a maximum. We're not sure, we don't need to worry about whether it's a global maximum or a local maximum. We just say it's a maximum turning point. So I'll write that there, maximum turning point. With our other one, when x equals 8, I would do the same thing. So x, first derivative, x equals 8 in the middle, so something a little bit smaller than 8, something a little bit bigger than 8, and put those back into the first derivative. So when you put 8 in, you will get 0. It's still a good idea to put 8 in. I have had equations come out before where I put it back in and it wasn't 0. It's very unusual, but it can happen. If you put in 7.9 back into here, you get a negative answer. If you put 8.1 back into the derivative, you get a positive answer. So let's draw those gradients. So negative, 0, positive. It is a minimum turning point. Minimum turning point.